Good morning. We're going to dive into Unit 6, Lesson 4, and look at how do we find all of the solutions to a polynomial function, both real and complex, because you can't see all of these on a graphing calculator due to the complex roots as well. All right, so pay close attention to the directions today as far as what the questions are asking, so you know what you're supposed to do. We're going to look at what's called rational zero theorem, remainder theorem, and then how to write an equation of polynomial given its zeros. So being able to know what the question is asking you. And we're going to start out with a rational zero theorem, and this gives you a potential list of solutions. And it lists plus or minus P over Q, where P is the factors of the constant, and Q is the factors of the lead coefficient. So the factors of this front one and then the factors of this top one. Okay, so being really good at factoring and knowing your factor pairs is helpful for this. So if a question is asking you to list all possible rational zeros, then you're going to look at your constant here, 12. And so P is plus or minus. I'm just going to put this 1 and then plus or minus 12. And I'm just going to list my pairs. So 2 and 6, 3 and 4. And then Q will be 1, 2, 3, and 6. All right. So those are our P's and our Q's. Now we need to list every P over every Q. So we go through, and I'm just going to put the plus or minus out front here. We have 1 over 1, which is 1, then 1 over 2, then 1 over 3, and 1 over 6. All right, and then we go to the next P. We get 2 over 1, which is 2. 2 over 2 reduces to 1, so we don't need to list that one. And we get 2 over 3. 2 over 6 reduces to 1 over 3. So then we can go to the 3. 3 over 2. 3 over 3 and 3 over 6 are already listed. And so you just keep going through your list until you have all of them. 4 over 2 is listed, 4 over 3. 4 over 6 reduces to 2 over 3. 6, that's 3, that's 2, that's 1. And then 12, that's 6, that's 4, that's 2. And so then that's it. So when it says list all possible rational zeros for this quadratic, this is your list. All right, that's not to say all of those are zeros, but if it is a zero, it will be in that list. So to check if any of these are actually zeros, you're going to do one of two things. Okay, you can sit here and plug each number into synthetic division until you get a zero remainder, and that tells you it's a zero. Or you can graph it in a graphing calculator, find a zero, and then use synthetic division to reduce your quadratic or your polynomial down to a quadratic. Okay, so remember from, which is the way I would recommend doing it, remember from lesson 3 that if C is a zero, then x minus c is a factor. of your function. And so we can use our list of potential zeros to find which one has a zero remainder and then convert that into a factor if we need to. We can go either way. Then you have your zeros theorem. Polynomials of any degree greater than or equal to 1 will have exactly n zeros counting multiplicity. And so if you have something to the 5th power, it will have 5 zeros. If you have something to the 7th power, it will have 7 zeros, and so on and so forth. So keep in mind you have to count multiplicity with that when you're doing that. All right, so you're going to do a complete factorization. Such that you have p of x equals to all of these factors. And you can factor with your i's now. So if you have plus or minus 2i as one of your zeros or two of your zeros, then you just write that as a factor of x plus 2i and x minus 2i. To get rid of the i's, you would just FOIL that, and you would have another factor as well. So depending on if you want i's in your answer or not. Okay, so we're going to just look at each problem here and find all possible rational zeros, and then I'm going to show you how to find the zeros themselves. So just solving this out. So first we list p over q plus or minus, and so my factors of p are 1, 2, 4, 8, and 16. Q is just 1. And so we have plus or minus 1, 2, 4, 8, and 16. Since those are all just over 1, then my list of possible rational zeros is just my p list, essentially. Okay. Then we're going to find all of the zeros. So this is where you can either, so I have p of x, I tried to colors there, didn't I? X to the 4th plus 8x squared plus 16. If this is factorable, then go ahead and factor it. So this breaks down into x squared plus 4 and x squared plus 4. It's a perfect square trinomial. Both of these will solve the same because we have x squared plus 4 with a multiplicity of 2. All right, if we solve this out, we get x squared equals -4, so x equals plus or minus 2i, which then also has a multiplicity of 2. Okay, so each of those has a multiplicity of 2, so our final factored form of this, because I have x equals 2i and I have x equals -2i, each with a multiplicity of 2. And 2 times 2 is 4, so I have x plus 2i squared and x minus 2i squared. So there's my 4th degree completely factored, showing my zeros, because if I see my factors, then I know what my zeros are. And so when it asks you to write complete factorization, this is what it's looking for. Okay, using your zeros to write that in factored form. Okay, so if it's factorable, then go ahead and try to factor it first before we resort to other methods. So go ahead and try this one. This one is also factorable. So you can see these are the zeros and none of them are repeated, so all of them have a multiplicity of 1. And so when we write out the factorization via x plus root 2, x minus root 2, x plus I, and x minus I. Now, we haven't really had to show this yet. This is the factorization. But keep in mind, you're switching the signs of the zeros when you put them in the factors. And so, for example, this one doesn't factor all the way down. It's a difference of 2 cubes. So it factors as x minus 4 and x squared plus 4x plus 16. So one of our factors for our factorization will be x minus 4, but we need to be able to find the rest of the zeros. So your P over Q list, it's just factors of 64 because our Q is 1. So we have 1, 2, 4, 8, 16, 32, and 64. Right? Just to kind of show how this works here, if we use synthetic division with the 4, knowing that x equals 4 is the 0 of our function, then we have 1, 0, 0, negative 64. Remember your placeholders. So we bring down the 1, multiply up, add, multiply, add, multiply, and add. You should get a 0 remainder for these. But if we're finding all the zeros, and what we have left here is x squared plus 4x plus 16, which we see if we use our difference of cubes factoring, then you know that this doesn't factor any further. There's nothing that multiplies to 16 and adds to 4. And we want to find all of our solutions. So we're going to have to plug this into quadratic formula and solve it out. Okay, so all right, so simplifying that down to this point, we get a negative 48 under our radicals. So what that means is that, I'm going to bring this up here, we have negative 4 plus or minus 4i, because it was negative, root 3 all over 2, which then reduces to negative 4 plus or minus 2i root 3. Oh, sorry, negative 2 plus or minus 2i root 3. Reduce everything by 2. Okay, so those are our zeros, and we need to put that in factored form. So we have P of x is equal to our original factor here that goes with this 0, x minus 4. And then we have x minus our 0 here, negative 2 plus 2i root 3. And then we have x minus negative 2 minus 2i root 3. All right, so this whole thing is a 0, so this whole thing needs to go in your factor. Okay, and this is your factorization of this polynomial. Okay, you could simplify it a little bit further and distribute this negative sign and drop your parentheses, but there's really no big need for that at this moment. Okay, so tying this all together, Synthetic division is not really necessary for that last one because we can factor it down to an x squared. When we have an x to the fourth, and something like this that's not factorable because we have an odd number of terms, that's when we need to rely on our possible rational zeros in our graphing calculator. So our Q, shallows will work here. So our Q is plus or minus 1, and our P is plus or minus 2. So our possible, or excuse me, 1 and 2, our possible rational zeros are a list of our P's anytime your Q is 1. All right. Well, if you look at your graphing calculator and type this in, and I've typed in the rest of them from the notes, but I'm just graphing this first one here. Then you can see, well, this one crosses at both -2 and at +1. And so those are both zeros for this function. Oh, goodness. So you pick one of those, which you set up synthetic division with it. So I'm just going to start with -2. And so I have 1, 1, -1, 1, -2. I don't need any placeholders with this one because I have all of my terms counting, starting with the 4 all the way down. But the synthetic division process is the same as always. I bring down 1, I multiply, add, multiply, add, multiply, add, multiply, add. This number here should always be 0 if you've done this right. Okay. Now, what I've just accomplished is getting this down to an x to the third. All right, well, that still, again, doesn't help me. I do only have 4 terms now, so I can attempt to like factor by grouping. But I know that it has another 0 at 1. So instead, I'm just going to keep dividing. I'm just going to draw my line again and divide by 1. All right, so the first term comes down. 1 times 1 is 1. Add, multiply, add, multiply, add. And once again, I have a remainder of 0, showing me that it did, in fact, cross at 1. So 1 and -2 are both zeros of my function. I've now successfully converted this down to an x squared. This would be my x, and this would be my constant. So I can rewrite this as x squared plus 1. All right, as my last factor. Well, if that's a factor, I'm going to set that equal to 0 and solve it out. So x squared is -1, x is equal to plus or minus I. Okay, so my zeros for this function are the original -2 and 1 that I found, but also I and -I. And so I'm going to take those zeros, my very last step here, and put them into a factorization. Oops, I don't know what the colon. Of x plus 2, remember you switch signs for your factors, x minus 1, x plus I, and x minus I. All right, if x minus 2 is a factor, then x plus, or excuse me, is a 0, then x plus 2 is a factor. Okay, so I want you to go ahead and do the same thing with this problem. So try this one on your own, please. Okay, so go ahead and check your work here. And remember that when you find your zeros, and so this crossed at -2 and 5, you can start with either one of those in terms of synthetic division. But each time you divide, it reduces the exponent by 1. And so when I go through in this -2, I should get a remainder of 0 always. When I'm doing this, or it doesn't actually cross. but that reduces it from an x to the fourth. So that's really hard to read there. To an x to the third. Well, I need to reduce that again before I can solve it with any other method. So the 5 goes in as well. So I reduce that then to an x squared. So then I end up with x squared minus 2x minus 1. Again, that remainder being 0. Okay, so remember, once you have that, it counts down. So squared, linear, constant. I just plugged this into quadratic formula. And watch your signs here, and reduced it all the way down to my zeros. So my zeros is 1 plus square root of 2 and 1 minus square root of 2 when you write that as 2 separate roots. I still have my negative 2 and my 5 that I started with. All right, so writing that in a factorization, I have x plus 2. Remember, the signs change. Then x minus 5, and then x minus 1 plus root 2, and x minus 1 minus root 2. We're going to look at a better way to express these in just a moment. So we write them in what's called standard form. That's not quite right there yet. Okay, you don't have to stop at x squared. If something continues to factor or has more than one place, more than 2 places where it crosses and reduces all the way down, you're absolutely welcome to do that. In this problem in particular, we have an actual Q. We have our P. If you once again look at your graphing calculator for this, I'm just going to switch which one mine is graphing here. And you can see that this one crosses at 3 spots. It crosses actually at 4 spots, but a few where I can tell where it is. I see that it crosses at -3. I can see that it crosses at 1. It looks like it also crosses at 3. And it looks like it crosses at somewhere between 0 and -1. All right, well, if we look at our possible rational functions, our p's over q's, or possible rational zeros, excuse me, we have 1 and then 1/2, and then 3 and 3/2, and then 9 and 9/2. All right, so we do have values between 0 and 1 that we could possibly use. So starting this out, and you can just pick any one that you want. We saw that it crossed at 3, so 2, -1, -19, 9, and 9. No placeholders needed. Bring down, multiply, add, all the way down. Remember that you should get a 0 as a remainder, or you've done something wrong, or you read your calculator wrong in terms of where it crossed. You can just continue with a different 0 that you found. So keep it, this was x to the 4th. We're now at the x to the 3rd line. If I reduce this again, then I'm at the x to the squared line. So you could stop here and use quadratic formula, but I could see on the graph that it also crossed at -1/2. And so I could just do this again. Don't be scared of the fractions. They have a nice way of working out. 1/2 of 2 is just 1, and so -1 makes this a 6. 1/2 of 6 is -3, and that makes that a 0. Once again, getting a 0. Well, this is the x line. So now I know that 2x plus 6 is really, I can keep that as a factor of my problem, but I want to look for the 0. So I'm going to subtract 6. And so x equals 2x equals -6. Oops, sorry. And then divide by 2, so x equals -3. So my zeros, and I saw that -3 on the graph, so I could have even gone one more and and reduce this down to nothing. My zeros are 3, -1, or excuse me, +1, -1/2, and -3. Well, when I put that into a factorization, I have my factors of x minus 3, x minus 1, x minus 1/2, and x plus 3, right? This one needs to change. And when I put this in standard form, I'm not going to have any fractions in my factors. And so I do x minus 3, x minus 1. All of these just have a multiplicity of 1. This 2 is going to move to the front, like I'm multiplying everything in this factor by 2. And then I've got it. Okay, so there's my factorization for this problem. All right. All right, and then last thing, conjugate zeros theorem. We talked about conjugates of imaginary numbers yesterday. We have a plus bi goes to a minus bi. So if either of these are zeros, then the opposite one is automatically a zero. So if you end up with a plus bi, you should always also have a minus bi. This is also true for radicals. All right, so if you end up with something like 1 plus 2 root 3, then you should also have 1 minus 2 root 3. Okay, almost done here. Being able to find a polynomial in standard form with integer coefficients that follows the given conditions, you're going to get what degree this should have. So you should end up with a total degree of 4 or 4 factors, counting your multiplicity. If you know the zeros, you should be able to rewrite those as factors. And then, again, take into account multiplicity. Your leading coefficient, if you have like p of x equals, you're going to have like a, x minus c, x minus b, and so on and so forth. Your a is your lead coefficient. Okay, so we're writing a factorization given these zeros of this function. Okay, so here goes. So we have zeros at 1 minus 4i, which means that we also have 1 plus 4i. And then we have 0 at -3. This one has a multiplicity of 2. Okay, so the first thing we need to do is write our factors. So the factor that goes with this 0 is x minus 1 minus 4i. Okay, remember, you do x minus c. So this one is x minus 1 plus 4i. And then this one will be x plus 3. Multiplicity of 2 means it has a 2 exponent. Okay, the only thing here that we're going to do a little bit different that we didn't do on previous pages is we are going to go ahead and distribute our negative and regroup it into real versus imaginary terms. And so we talked about that a little bit with our imaginary numbers, how we need to separate it with your A term, your real numbers, and your imaginary numbers. Okay, so that makes this one then x minus 1 plus 4i, and that would be that factor. And then the other one will be x minus 1. So notice that that part, the real part, is the same. And then minus 4i. Same thing with radicals here. And then we have our x plus 3 squared. So right now we have a multiplicity of 4. And then the last thing we need to tack on is we were given a lead coefficient of -8. Your LC just goes right up in the front there. This is p of x, and that's your final answer. Okay, so again, 2, 3, 4, we have this to the 4th power. If you FOIL all this stuff out, this lead coefficient will stay the lead coefficient because it will end up 8x to the 4th. Okay. So go ahead and give this one a shot. Okay, so here is your factorization of this one. Nothing was given a multiplicity. Here's what it would look like if you FOILed it out, just to show you that I still have a lead coefficient of 48 and a degree of 4. You have 1, 2, 3, 4 degrees here. And I just wanted to show you that this is not a required step. All right. Also note, you should be able to pick out zeros from a graph. Look for your x-intercept. And your behavior. Is it crossing or just touching? So that you can think of your multiplicity. Okay. And that was a really long video, and I apologize for that, but that is it. If you have any questions, please let me know.